Hey class, this is Mr. Schmidt. I'm doing a recap of our September 25th Friday lesson on graphing motion. I know a few people had internet problems, so hopefully this clears up any gaps that you may have had. All right, so we were talking graphing motion, but before we got to any of that, I asked a question. This is to test your science ability to claim evidence reasoning. Okay, so the question was, starting at the North Pole, how far could you walk in a straight line before you ran into something? So the key part of this is, can you get your evidence and reasoning to support your claim? So some students asked, well, can I swim? I said, no, it has to be walking. Okay, that means if there's something that you would like fall in or you couldn't walk over, that would all count. Okay, I then gave students some time before we went on to the next thing. A couple things to keep in mind in terms of boundary conditions. Some people are like, well, how did I get there? I'm too cold, I freeze to death. Well, you'd probably keep moving to stay warm for as long as you'd stay alive. You wouldn't just like sit down because you're cold. But you might get stopped by a barrier is the issue. So a couple things I looked at for boundary conditions is Greenland is one of the closest to the geographic North Pole. So we're talking geographic North Pole, not the magnetic North Pole. And I looked at if we go north to south in Greenland, that is over 1,000 miles. So if we're talking orders of magnitude, so that's in the 1,000 range, whether it's kilometers or miles. And again, extending farther from the northern part of Greenland to the North Pole, we're still with less than 10,000 miles, right? We're still just over 2,000 kilometers, maybe 3,000 kilometers, North Pole to the southern tip of Greenland. So my thinking was that would be the closest land feature to the ice pack and the most likely to guarantee a year-round connection to the ice pack. Okay, the other boundary condition to think about is the original definition of a meter is that 10 million meters was the distance from the North Pole to the equator, okay? Or 10,000 kilometers was the original set for the North Pole to the equator. Now that we've gotten better at measuring meters and measuring the Earth, we have since changed that, because when they originally did this, they then made a golden meter, a rod that sat in France. They said, this is a meter, and that became the new standard. No longer was based on Earth, okay? And everyone had to be compared to these golden meters, and eventually we changed our definition slightly, and we see that about 10,010 or 10,030 is somewhere around our distance from the North Pole to the equator. Okay, so again, the Earth is kind of a bulbous, not perfectly round thing, and our definitions of meters and definition of the Earth have changed. But so that puts a boundary condition of if we were just to reach the closest land feature and go to the southern tip of that, that would put us just over 1,000. And you know, if for some miracle we got all the way to the equator, that would put us at 10,000 per kilometers. So that would be the upper range when we're looking at our evidence and then our reasoning, and then that would lead us to our claim. Okay, so that was just our intro. But what we really want to do is use our evidence and reasoning to start doing some graphing as we graph motion. And we look at how displacement, velocity, and acceleration, how those graphs stack up, okay? So when we look at the distance versus time graph, well, then we're doing rise over run, and distance over time is velocity. And when we do our velocity time graph, rise over run, velocity over time is acceleration. So again, displacement, velocity, acceleration. As we go down, the slopes will tell us the next one. The interesting thing is, as we go up, if we do velocity times time, we get distance. So if we do area, velocity times time, the area will take us from acceleration to velocity to distance or displacement, which is what our assignment's going to be for. Okay, so we looked at this graph here. They do a great job explaining it in hyperphysics. Okay, again, you can just read over this on the website, but for your auditory learners, what we're looking at here, it curves up, which means the slope is increasing. So we need our velocity to increase. Here, it's a straight line, which means our slope does not change. So we need our velocity to stay constant, okay, or horizontal. Here it curves down to 0. So here we need the slope to hit 0 here, which means at 15 seconds, it went up, and for an instantaneous moment, it stopped moving, and the velocity then moved downward, okay? There's no like stair step or gap where it stays at 0 velocity. It is purely an instantaneous moment where those two lines cross, okay? All right, now here we still have it curving down, which means it's still, the line continues. And this line is going to be very common in physics. If we throw a tennis ball or a volleyball or anything else that goes in the air, and once it leaves your hand or it stops getting a force on it, then it's going to follow a parabolic arc, and it's going to, the force of gravity is going to act on it, very similar to this line. Okay, the slope will be slightly different, but the shape is going to be identical. Okay, then it looks like someone catches the ball here. Okay, so it goes from going down to stopped. So here we have this reaching a 0 velocity, and then it sits in her arms, and then, like I said, the ball or whatever has now been caught, and it stays at a stable position. Okay, now this is 40 meters up in the air, so I don't know if it's something you'd want to catch or not. But that's the way it's drawn. Okay, now if we keep going down, again, the slope of one line tells us the position of the next line. So this is all sloped at, looks like it goes up, so go up 16 in a distance or over 4 seconds. Okay, so 16 over 4, rise over run, gives us 4. Okay, here, the slope is 0, so it drops down to 0. Okay, and then at somewhere 6, 7 seconds, it starts to tilt downwards. Again, that's a straight line passing through 15. So it stays at a constant negative acceleration. Okay, and then at 23 seconds is when she caught the ball, and therefore the acceleration is going to jump up. And it's going to go at, what's the slope of this one? Looks like it's back to 4. Looks like it's going from negative 16 up to 0 in the space of 4 seconds. Okay, so as we go through these, from displacement to velocity to acceleration, we just look at the slope to find out the one below it. Okay, but when we go backwards, okay, so this whole thing, by the way, in case you didn't know, Newton invented one form of calculus in order to figure this out. He called these derivatives to go from distance to velocity to acceleration. He took the derivative of each one. He found the slope of one to graph the next one. He found the slope of the velocity to graph the acceleration. Okay, to do the opposite, you do integrals, which you're looking at areas. Okay, so here we have the area of this first rectangle. It was a 4 by 4, which means the first point needs to be at 16. Okay, this 4 by 4 also, the line is horizontal, which means the slope of the next one needs to be a straight line. Okay, so we see a straight line going to 16. Okay, from 4 seconds to 8 seconds, the area is 0, so it's going to increase 0 meters per second, okay? And then we keep going. Here it has an area of -2, and it goes over, looks like, what was that, 10, 15 seconds. Okay, so then you'd have to take that -2 times 15, and you would drop down 30 from one to the other. Okay, again, horizontal line on one point leads to a straight line, non-horizontal, on the next one, okay? And then we have one more box that's a 4x4. So that would have to bring us up 4x4, which is 16. That will have to bring us up 16 and it brings us back to the original position. So now we see we went from very blocky and we're going to keep doing integrals, which is going to get things more curved, okay? Because now when we have this diagonal line, it goes over 4 and up, well, that's 15, okay? And we have to find the area of this, so 1/2 base times height. So we're going to go up about 30 here. And again, the slope starts at 0, and then the slope's going to end at 15. So it has to start at 0 and then curve upward to get to that point we just marked, okay? Here we have, it goes over from 4 seconds to 7 seconds maybe. So it goes over 3 and up 15. So it's a rectangle, so we can just do 3 times 15. It's going to go up another 30, okay? Because this is a horizontal line, that means the slope does not change. It's a straight line here, okay? And then as we go through this third box, the triangle, so it's a triangle, so we're going to have to do 1/2 base times height, and we continue that trend. Okay, so now we're coming back to our notes here. So like I said, we had a position, velocity, acceleration. You could keep taking derivatives and you get jerk, snap, crackle, pop. Okay, so obviously there's some physicist or mathematician that had to sit down and think of these names. And in fact, it goes pop, lock, and drop if you keep going. Most people, after they get past acceleration, just call it third derivative, fourth derivative, fifth derivative. I was looking at these. There is a tie-in to like driver's ed. When you come to a stop sign, the normal directions are to come to a complete stop, including the lurch, which means not only is your velocity 0, but your acceleration has gone to 0. So that is like doing the next derivative, bringing it down to your jerk. Okay, and then you're supposed to proceed through your stop sign. All right, so we had a number of assignments here going through this. So our next thing is to look at the graphing motion assignment, which comes in 2 parts. All right, the first one is the transforming, and then we'll do a little bit of comparing here. So the transforming one, they give you the velocity and you have to draw the other 2 charts. Okay, so I gave students what ended up being about a 20-minute time to draw these. So if you haven't done it, you should take a 20-minute break and try to do this yourself. Okay, once you're done with that, come back here. You see what we have to do is find this area and plot it up here. Okay, so this is for, I'm going to switch to my pen so we get a little bit clearer. Okay. All right, so what we have here is 4. Makes that a little bit better. All right, we have 4 here, and it goes over 4. So we do 1/2 base times height. All right. So 4 times 4 is 16. 1/2 of that is 8, which means this is above the 0, above the y-axis. So it's going to go up 8. So when we're at 4 seconds, we need to go up 8, which puts us somewhere in this ballpark. Now it started high, which means there's going to be an increased slope here, and then ends up at 0, which means there's going to be a 0 slope there. So there's going to be a curve happening. Okay, then let's switch to the next one, which means now we have a similar triangle. It went down -4 and included another 4 seconds. Okay, so 1/2 base times height here. Okay, 4 times -4, -16, 1/2 of that. Now we go down 8. Okay, so that area was -8. So now we're here. Okay, again, we started at 0 slope and then we ended with a very negative slope. So we're going to see that curve there. Okay, then we continue the process. Here we have another 4 seconds and it's another 4. This time it's a square, so we just do 4 times 4 is 16. So this area here is 16. So now we have to go over 4, okay, and down 16, which should put us 5, 10, 15, 5, 10, 15, 16. Yeah, it should put us right in here, okay? And that, the slope, that this number did not change. It was always -4. So we need to continue this -4 slope the entire time, which means you also could have skipped figuring out the point and just stayed with the slope. Okay. Now we have another 4x4 triangle, which means it's going to go down. Remember, we're still below the horizontal. We're still below the axes. So it's going to go still in the negative direction. And it's again a -8 area. So now we need to go down another 8 from there. Okay, and now we're at 16 and we're somewhere around here going down another 8. Okay, we returned to 0 displace or 0 velocity, so we need to return to a 0 slope here. Okay, and then we have a 0 position change here this entire time. So it does not move for that entire time. Okay. And then we're back into the positives. Okay. So now this should look a lot like that first one. 4x4, it's going to go up 8. Okay. And it's going to hit at 24. Okay. So again, it's going to curve. It starts at a 0 slope and it ends at a slope of 4. Okay, and then it keeps going with a slope of 4. So we do one more area here. We get a height of 4, and this is 24 to 30. So that would be 6. So 4 times 6 is 24. So that should take us up this way again. Okay, remember we have a slope of 4 here, so you could just do a +4 slope and just continue that line that way. So if we're looking at these, this should be a straight line because it's coming across this way. This should be a straight line because, again, the velocity did not change. Okay, velocity did not change, so that should be a straight line. Can't see my numbers anymore. From 8 to 12. Right, from 8 to 12 was a straight line. Yeah, that sounds right. That was a straight line, okay? So those 3 points should have been straight lines because those were all constant velocities. All right, so I'm going to erase these for a second, and then we're going to come back and look at the acceleration. Okay. What's going on here? So what we're looking at here is the velocities and the acceleration. So hopefully we were doing area before. Now we're going to find slope to go down. So here we went down 4 and we went over 4. So that's a slope of -1. Okay, so now we're going to take our acceleration and go -1. Okay, and then we still went down 4. We went over 4. So that means this acceleration did not change for the first 8 seconds. Okay, then it went over 4 and up 0. So our slope is 0. Okay, over to 12 seconds. Okay, and then it went, let's see, we're changing our colors here. Over 4 and up 4. So now it's going to have a positive acceleration. Okay, I think it was right here, up to 1. And then at 16, drops back down. Okay. Now, once again, up 0, so it has a 0 acceleration. Okay. And then it went up 4 and over 4. So we're just doing rise over run. It's the only thing I'm repeating to myself over and over again. So it went up 4 and over 4. So again, we see this. Okay, and then finally we have up 4 and over the rest of the way. So now we're back to there. Okay. Okay, we're back here. Hopefully it captured all of that of as we go down 4 and over 4, that gave us a negative slope. As we went up 4 and over 4, that gave us a positive slope. And as if we don't go up or down at all, that gives us a 0 slope. Okay, so then we can wrap up here and look at the beginnings of our last worksheet, which is the compare. Okay, so now we're trying to compare the displacement, velocity, and time. Okay, so for the y-intercept of displacement, okay, so once again, what color haven't I used? Oh, didn't use green up there. Okay, so at 0 displacement, that means we're back at the origin. So that's what you would put here. You've returned to original position or back to the origin. Okay, at 0 velocity, that means you're not moving. Okay, so you could be at any position, but you're not moving. Okay, that's your velocity time. That's what you're going to put here. And then if we scroll down, what's happening at our 0 acceleration? That means we're not speeding up or slowing down. Sometimes we are not moving at all, okay? Or sometimes we're simply not accelerating. We're not speeding up or slowing down, okay? So that's what we're going to put over here, is that we're not speeding up or slowing down. We might be at rest, okay? So that's how we're going to fill this out. And if you're paying attention, you actually can't, oop. All right, you're back at your answer key over here. Okay, so that was the assignment. There was a previous assignment that also needed to happen, but if you're watching this video, you're probably on top of it. The Canvas tour asked you for a few screenshots as well. Okay, so my forehead back on the shot here. With that, hopefully you have the beginnings of these different graphs. Like I told the class, these series of graphs, being able to translate them and calculate them, definitely shows up in the AP exam, which means I definitely have to carry them on my exams as well. It's the beginning. It's one of the times where we make the most mistakes. So let yourself make mistakes, keep practicing, by the time it really matters, we'll get it right. Okay, so with that, have a good day, and I hope to see you soon.